Finally, we're going to round up Chapter 6 by talking about intermolecular forces. Let's talk a little bit about the definition of intermolecular forces. Inter meaning outside, so forces outside of the molecule. If I'm looking at just one molecule, those types of forces are intra, between the atoms in the molecule. But inter, with INTER, intermolecular forces are forces between molecules in the bulk. So they're electrostatic attractions between the particles of any substance that I'm looking at. They can be ions, they can be molecules, they can be atoms, etc. Now, ions, since they have full charges, they have attractive forces that are very strong because they have full separation of charge. When I'm talking about molecules, those molecules that are polar have stronger electrostatic attractions than those molecules that are nonpolar, or atoms, because atoms are not charged. They're neutral, and so they do not have the same type of attractions as polar molecules or ions. Atoms have only, so in polar molecules, have partial charges. However, they are weaker than those between full charges, but they're strong enough that they determine many of the properties of the substance, such as whether that substance is a solid, liquid, or gas at room temperature, etc., etc. So the stronger the attraction between the molecules, the higher the likelihood that it will be found as a solid at room temperature or as a liquid versus a gas. We will begin the discussion on intermolecular forces by introducing dispersion forces. These are forces that exist between nonpolar atoms or nonpolar molecules, and they are the weakest of all intermolecular forces. Now, we talked about polar molecules having a separation of charge. Now, it's not a full separation like an ionic molecule or an ionic compound, but polar molecules have that permanent dipole because of the electronegativity difference between the two atoms in the molecule. What happens in a nonpolar molecule? I don't have that separation of charge. At least I don't have it permanently. But what I do have is a separation of charge that is caused by electrons moving around the atoms in the molecule. This creates what we call an instantaneous dipole. So it's a dipole that it's temporary. It exists right now, but then the next instant it's gone. And how does that occur? Well, if you think about, if this is my molecule right here, and I have electrons that are orbiting around those two atoms in my molecule, well, in one instant, it may just happen that all the trajectories of all the electrons that are orbiting happen to take them on one side of that molecule for just this instant. Well, even that little bit can impart a negative charge on the density. So in the area where I have a higher density of my electrons, just because they happen to be moving closer together in this instance, and I have less of a negative charge on the other side. That gives me a temporary dipole, a temporary separation of charge, where the red has the partial negative charge, and the blue, the partial positive charge. Now, if that happens in my molecule here, right, I have a partial negative charge here, a partial positive charge here. Well, if you think that if I have another molecule that is right next to it, is very close, remember that like repels like, so like charges repel, but opposite charges attract. So if I have a partial positive charge on this end of that molecule, that is going to attract the electrons towards that end. So it's going to give the next molecule that is close to it a partial negative charge on that end and a partial positive charge on this end. And so you can see how one molecule with an instantaneous dipole or a temporary dipole can induce other molecules to form temporary dipoles as well, if they're close enough. And this is called a dispersion force. These are the temporary instantaneous dipoles that are formed, and then they induce a dipole on the molecules that are next to them. Now, these are now here and gone the next instant, so they're not permanent, and therefore the dispersion forces, also known as London dispersion forces or van der Waals interaction, these are not the strongest because the dipoles are not permanent, they're temporary. Now, the strength of dispersion forces depends on the molar mass of the molecules. So the higher the molar mass, the stronger the dispersion force is going to be. And that is how we're going to look at molecules when we compare how strong the dispersion forces are in those molecules. If we have to compare several of them, we look to see if whoever has the highest molar mass, that is going to have the higher dispersion force. So here's an example problem or a sample problem here. In each pair of nonpolar molecules, so it tells you that they're nonpolar, choose the substance with the stronger dispersion forces. Those that have higher molar mass, are going to have stronger dispersion forces. I will give you some time for you to try these. The next intermolecular force that we're going to talk about is dipole-dipole forces or dipole-dipole interactions. These, once again, are attractive forces, but these are found between polar molecules this time, not nonpolar. So polar molecules that have permanent dipoles. These are molecules that are diatomic that contain elements that have different electronegativity values, and they have an unequal distribution of electron density. Therefore, that causes them to have partial charges, partial positive charge, partial negative charges. These are there to stay though. They're not instantaneous or temporary because the electronegativity differences are larger than 0.5, so they're 0.5 and smaller than 2.0. And these forces are responsible for holding the molecules together in a liquid or even in a solid at room temperature. Now, the dipole-dipole interactions are going to depend on the strength of the dipole. So the more polar the molecule, so the larger the electronegativity difference is going to be between the atoms in that molecule, the stronger the dipole-dipole interaction is going to be. So if I am comparing dipole-dipole interactions in several different molecules, the first thing that I'm going to do is determine whether I have a polar molecule. If the problem tells me, then I can assume that the molecules are polar and it's a given. But what I need to do to figure out the strength of the dipole-dipole interactions is to do electronegativity differences. The larger the electronegativity difference, the higher the dipole-dipole strength, the stronger the dipole-dipole interaction is going to be. So here's another sample problem. Determine whether these molecules exhibit dipole-dipole forces. Now, when I'm looking at these molecules, I am going to do, first of all, to draw Lewis dot structures for these, determine what the shape of the molecule is going to be, and then that will tell me whether I have a polar molecule or a nonpolar molecule. In this case, for example, if I have Br2, that is really simple to do. You can do the Lewis dot structure, but it's a very simple case because I have a diatomic molecule that is made up of exactly the same two atoms. So that is not going to be a polar molecule. For these three, you're going to have to determine the shape of the molecule. And then, remember we talked about it in the previous video? From the shape, you're going to look and see, do I have exactly the same atoms that are bonded to my central atom? Do I have any lone pairs? That is going to determine whether the molecule is polar or nonpolar. And then, if it is a polar molecule, it's going to have dipole-dipole interactions. If it isn't, it's going to have dispersion forces. And which one of the two is the strongest? So then you can determine which one have dipole-dipole interactions. The last intermolecular force that we're going to introduce is hydrogen bonding. Hydrogen bonding is really a special case of the dipole-dipole interactions. It is only found, so very, very important, it is only found in those molecules that contain these three specific bonds. So a nitrogen that is directly bonded to a hydrogen, an oxygen directly bonded to a hydrogen, or a fluorine that is directly bonded to a hydrogen, which in this case, it's only HF. There aren't any other molecules other than HF. But hydrogen bonding is found in molecules that contain these three bonds specifically. So the nitrogen, oxygen, or fluorine have to be bonded directly to the hydrogen. They are stronger than regular dipole-dipole interactions. In this picture here, we have hydrogen bonding that is occurring between hydrogen fluoride molecules, and you can see how strong the dipoles are and what the interaction is, and you can see how regular those the arrangement of the molecules is. That makes this bond even stronger than a dipole-dipole, regular dipole-dipole. So nitrogen, oxygen, and fluorine have some of the highest electronegativity values in that table. And so when you do the electronegativity values or difference between an NH bond, OH bond, or FH bond, that difference is going to be very large. And that makes these stronger generally than the dipole-dipole interactions of other polar bonds. So you can see how we have negative charges and positive charges that are almost, not quite, but fully separated because those electronegativity differences are so large. Which of the following molecules exhibit hydrogen bonding? Figure out how those atoms are bonded to the central atom and figure out whether you have a nitrogen directly bonded to a hydrogen, an oxygen directly bonded to a hydrogen, or a fluorine directly bonded to a hydrogen. And then determine whether you have hydrogen bonding or not. Let's review intermolecular forces. First of all, intermolecular forces are additive. All molecules exhibit dispersion forces. Even polar molecules, or those that hydrogen bond, have dispersion forces because they can have temporary dipoles on top of their regular dipoles, depending on the distribution of the electrons in every instant. But when I'm looking at molecules that have dipole-dipole interactions because they have permanent dipoles, they also have dispersion forces. Therefore, dipole-dipole molecules that have dipole interactions have dispersion forces plus dipole-dipole interactions. However, it's kind of thinking about, if I'm weighing an elephant and then I add a fly to the elephant, these are so much bigger than the dispersion forces. So even though we're adding them together, the most important one becomes the dipole-dipole interaction, not necessarily the dispersion forces. But know that they are additive. The strength of the intermolecular forces increases from dispersion forces to dipole-dipole interactions to hydrogen bonding. And then we would have ionic bonding over here and ionic to polar molecules over here, but we didn't talk about them. Now, this is a generalization and applies only to substances that have similar molar masses. So let's take a look here. If I'm comparing bromine, right, bromine has a molar mass of almost 160 grams per mole, is nonpolar, and it only exhibits dispersion forces and none other because it's a nonpolar molecule, and it is a liquid at room temperature. However, if I'm looking at iodine, it has a higher molecular mass, almost by 100 grams per mole. So its molar mass is 254 grams per mole. Even though it is nonpolar, but because it is so much larger, and remember we talked about how dispersion forces increase with increase in molar mass, because this is higher in molar mass, it exhibits dispersion forces that are stronger, and therefore it is a solid at room temperature versus a liquid. That bromine is a liquid versus iodine is a solid at room temperature, because even though they both have dispersion forces, the dispersion forces of iodine are larger because it has a greater molar mass. So dispersion forces typically are the weakest of the intermolecular forces, but they're still strong enough to hold molecules together in a liquid or in a solid state, depending at room temperature, such as the example that we looked at here. But this is the general strength of intermolecular forces. We go from dispersion, which are the weakest, to dipole-dipole, which are stronger, kind of in the middle, and hydrogen bonding, which is a special case of dipole-dipole interactions, being as the strongest of the three. Remember that these are additive, so whatever hydrogen bonds also has dipole-dipole and dispersion forces. What kind or kinds of intermolecular forces exist in these four molecules? First thing you need to do is draw Lewis dot structures to determine the molecular shape, and then figure out if you have polar molecules, If you do have polar molecules, do those molecules have an NH, an OH, or an FH bond that would make them have hydrogen bonding? So you will have to determine whether each of these molecules, if they have just dispersion forces or dispersion forces and dipole-dipole interactions, or dispersion forces and dipole-dipole interactions and hydrogen bonding.